Okay, so the sound lesson ends in a discussion about musical sounds. And it kind of starts with what musical sounds are, and it's kind of hard to define. Your book says musical sound creates a pleasant rather than an unpleasant sensation when striking the eardrum. Well, that's up to the person hearing it, whether it's pleasant or unpleasant. I might define it more as it's a series of specific notes that are arranged on purpose, but whatever your definition is for what makes a sound musical doesn't really matter, but we will talk later about some more concrete definitions for what makes harmonious notes, what makes sounds sound good when you play certain frequencies together. So we'll explain that. So it goes into talking about different musical instruments and how they work, and it breaks it into three categories based on how the sound is produced. So you have string instruments produced by a vibrating string, where characteristics about the string are changed to change different notes. Wind instruments, where you're making a column of air within inside the instrument, and the vibrations of that column of air is what makes the sound. And percussion, where one object is striking another and making it vibrate. So for string instruments, an important thing to know is how to change the frequency that's created when you vibrate the strings. So a lower frequency would be created with looser strings, and as you add more tension to the strings, you get higher frequencies. You can also compare the length of the string. A long string will give a lower frequency, and a shorter string will give a higher frequency. And the thickness of the string. So a thick string will give a lower frequency, and a thin string will give a higher frequency. And this is kind of an intersection of talking about things in everyday terms and in science terms. So we're talking about frequency here, and what you hear that as is the pitch of the note. So you have a low note or you have a high note, and you can determine that by the frequencies. So a low frequency is a low note, a high frequency is a high note. So changing these three things about the string would change the note that they play. In other words, changing the frequencies. And then with most string instruments, there's a sounding board that vibrates in resonance with the note being played to make it louder. So that's often just a part of the instrument, and in acoustic guitar, it's the body of the guitar, whereas the string plays over it, the vibration of the body amplifies that sound. Then we have wind instruments. They work by creating a column of air inside that we can vibrate. So we learned in the last section that if you have a tube or pipe, an open area where there's air inside, the length of the column of air will determine which frequencies or wavelengths of notes will vibrate and resonate inside of them. So we kind of looked at it in the last section as changing the length of the tube to match a certain frequency, but this is kind of the opposite. By changing the length of the tube, it's going to determine which frequency will actually vibrate. So if you blow into a wind instrument, so a flute or a trumpet or a clarinet like you see here, you're just putting a column of air into there. You're not blowing into it with a specific note. It's just general air. But by pressing the keys or holes on it, you're changing the size of the air column that's available, and that's going to make different frequencies within that moving column of air resonate. So as you blow into it, you're making lots of different frequencies, but by changing the keys, you're changing which frequencies are able to resonate within a column of air of that length. And then the last category was percussion instruments. They usually involve a stretched membrane that vibrates when struck. And most of the percussion instruments don't have a way to change the frequency, so you can't play different notes on them like you can with other instruments. Also, because of the complex vibrations that take place, it isn't usually a single definite note that you hear. You hit a drum, it's just kind of a noise. It's really several frequencies at once. So that's percussion. Now, when a string vibrates as a whole, its vibration is called the fundamental frequency. So something like this, where this is the whole length of the string, and it's just vibrating the entire string back and forth at once. So whatever frequency it moves at, that's the fundamental frequency. And then, in addition to that, you get additional patterns of vibration that occur with the fundamental frequency, and those are called overtones. So if you pluck a string on an instrument, you get this fundamental frequency, but you're also getting these other waves that happen on the same string at the same time. You can get wave patterns that look like this that are a little smaller, and those are called overtones. So those are very important. So on the next slide, we'll see how we measure those. So the frequency of a vibrating string is inversely proportional to its length. So what that means is if you if you cut the string in half, make it a smaller length, you're going to double the frequency. Or if you cut the string in thirds, it'll be 3 times the frequency. Harmonics are overtones with frequencies that are multiples of the fundamental frequency. So that's an important term from your book, harmonics. So for example, if our fundamental frequency here is 1000 hertz, if we cut the length that vibrates in half, so we make it vibrate with these 2 smaller waves instead, and they're half the size, the new frequency is 2000 hertz, and that's called the second harmonic. So you've got your fundamental frequency, you've got your second harmonic. The next one is, we're going to, again, use multiples of the fundamental frequency. So you take 1000 multiplied by 2, that's the second harmonic. 1000 multiplied by 3, that's the third harmonic. So you can see the wavelength is cut in thirds, and the frequency is tripled. And if we take 1000 hertz and we multiply it by 4, we get 4000, and we get our fourth harmonic. So our wavelength is cut into fourths, and our frequency is multiplied by 4. So we have actually a practice problem based on this. If a string vibrates at a fundamental frequency of 321 hertz, and it produces an overtone with a frequency of 693 hertz. This overtone is the blank harmonic, and what's its frequency? So if this is our fundamental frequency, the entire string is vibrating is 321 hertz. If we multiply that frequency by 2, we get 642 hertz. That's our second harmonic. If we multiply it by 3, we get 963 hertz. That's our third harmonic. So that's the number we're looking for, 963, and that's the third harmonic because we multiplied the original frequency by 3. And this overtone has a frequency equal to blank times the fundamental frequency. So 321 times 3 gives you 963, so it's 3 times. Okay, next part of this is characteristics for sound comparison. So some ways to kind of compare different musical notes would be first to compare their loudness. And the loudness is based on the amplitude of the sound waves, but what it is a measure of the energy that's put into the sound by its source. So if the source has more energy, the sound will have more energy, so you will experience that as being louder. The next one is kind of hard to explain. It's the quality of the sound wave. The quality of the sound is determined by the overtones it produces. So if you play a C sharp on a piano, and you play a C sharp on a flute, and you play a C sharp on a violin, and you play a C sharp on a trumpet, all 4 of those are going to sound different. It's the exact same note. They're going to be in perfect harmony, well, they're playing the same note, but you could hear the difference. You could tell the difference between the sound a piano makes and the sound a trumpet makes. And that is the quality of the sound. And again, that's caused by the overtones that it produces. So they're all playing that same fundamental frequency, but they're all making different patterns of overtones. So some of them sound more mellow, some of them sound more harsh, some of them are somewhere in between. And our third option here is pitch. And this is how we hear the frequency of the sound wave. So again, a pitch is low or high notes. It has nothing to do with how loud the sound is. There's just a low note or a high note. So we compare different pitches by comparing the ratios of their frequencies. So we find the frequency of the notes and compare their ratios, which we'll look at on the next slide. When we talk about musical scales, which is the notes that go together for a set of music, they're determined by the ratios of the frequencies of each note. So frequency is really important, especially comparing the frequencies of different notes to decide how they go together. So let's look at how that works. When you play two notes at the same time, they're component waves. And as we learned a couple sections ago, you have two components and they're going to interfere with each other. So they're going to sometimes cancel each other out, sometimes build each other up, that kind of thing. And it kind of makes a new resultant sound. So your component waves are going to make new patterns in the sound of the molecules that make the sound waves. And if those patterns are really irregular, the note is what we call discordant. So discordant would be play notes together that just sound terrible together. They sound really harsh. They're not good. They're not a chord or in the same scale. They're just random notes. The other opposite term for that is harmonious. So sounds that sound good when you play them together, notes that go together well, that make up a chord or the same part of a scale, those are called harmonious. So to determine the difference between them, discordant versus harmonious, without playing the sounds, how can you know whether they'll sound good together? The way to do that is to compare the frequencies of the original two or three notes you want to play together and the resulting waves that come from it. And if the ratio of any of the original numbers and the resultant waves are ratios with low numbers, it will be harmonious. Okay, so if you take the original waves and the resultant waves and you compare the ratios and you get nice numbers like 1 to 2 or 1 to 3 or 1 to 4, they're going to sound really good together. That's harmonious. If you compare those numbers and you get something really weird that doesn't reduce down, like 3 to 58 or 1 to 67, okay, those are kind of bigger numbers, weird fractions, those would be discordant. So again, if you play notes together that have frequencies that make ratios that are simple, like this, they'll sound good together, they'll be harmonious. And if you have frequencies where the ratios kind of are big and weird, you get discordant. They don't sound good together. So this brings us to putting all the notes together into a pattern that works. What we use mostly in Western music is the diatonic scale, which is scales made up of 8 notes. You may have heard people practicing singing do, re, mi, fa, sol, la, ti, do. That's a scale. Each of one of those notes is separated by a certain amount because there's certain frequencies. You can also see it really easily on a piano. There's a pattern that repeats. So the diatonic scale is the most harmonious ratios of frequencies. And we give each note a letter that goes from A to G, and then it repeats. So on our piano, we have A, B, C, D, E, F, G, and then it starts again at A, B, C. So every 8 notes, they repeat. And the simplest kind of way to look at it is in piano if you're playing in the key of C. So you start with the letter C. And it goes C, D, E, F, G, A, B, C. And the reason that we picked that one is because you play all of the larger white keys on the piano to get that scale. So in that key of C, the white keys are the 8 main notes, and the black keys are additional notes. They're called sharps and flats. So because of the way they're spaced out, the frequencies of them are spaced out, this is different if you play a different key. If you started with A and you went A, B, C, D, E, F, G, A, playing the white notes wouldn't sound good. There'd be a few that need to be messed up, and you need to incorporate some of these black keys instead. So we're not going to learn about all that, but you should have the general idea that the diatonic scale is 8 notes. They're supposed to be very harmonious together based on the ratios of their frequencies, 8 notes that repeat every 8 notes, and that if you're playing in C, it's just the white notes on the piano without incorporating any of the black ones. So that actually brings us to the end of this section. And if you're watching this later, here's how you can contact your instructors for any questions.